Hi everyone, my name is Aria, and I work alongside Whitroy as an electrical tutor. Before we begin, I want to make something clear about this audiobook. This is not a word-for-word reading of ASNZS 3000, 2018. The standard itself must always be read and followed exactly when you are doing electrical work or preparing for EWRB exam. What this audiobook does is take the key ideas from the standard and explain them in simple, spoken language, the kind of language you can listen to while driving, working, or revising. It helps you understand what the clauses mean, why the rules exist, and how they apply in real installations. So think of this as a learning companion, not a replacement for the actual standard. Alright, let's get started. Today we're moving into Section 2 of ASNZS 3000. This section is all about protecting people, property, and equipment by designing electrical installations the right way from the very beginning. We look at things like basic protection, fault protection, overcurrent protection, RCD protection, overvoltage, undervoltage, arc fault protection, and how switchboards must be built and installed. I'll explain each clause in simple language so you can understand the purpose behind the rules, not just the words. So let's get into it and make Section 2 easy to learn. Section 2, General Arrangement, Control, and Protection. This section explains the basic rules for choosing and installing switchgear and control gear. The aim is simple: the installation must be safe, reliable, and protected from faults. Clause 2.1, General. Clause 2.1.1, Application. This clause explains why Section 2 exists. It tells us that the switchgear and the control gear in any installation must be chosen and installed so the whole job meets the safety principles from Part 1 of ASNZS 3000. In simple terms, this clause says that the equipment controlling the installation must be suitable, must be safe, and must work properly under normal use. Clause 2.1.2, Selection and Installation. This clause explains what switchgear and control gear must be able to do. It says the equipment must allow us to control, isolate, and safely work on the installation. This includes turning off a whole installation, turning off a single circuit, or turning off one piece of equipment so we can test it, repair it, or check a fault. It also says the equipment must automatically disconnect the supply if something goes wrong. That includes an overload, a short circuit, or too much earth leakage current in the part of the installation being protected. The idea is simple: if there is a dangerous fault, the device must trip before someone gets hurt or the wiring is damaged. The clause also explains that the equipment must protect the installation from voltage problems, such as when the voltage drops too low or rises too high. This is to stop equipment from being damaged by poor supply conditions. The clause then reminds us that the switchgear and the control gear must be grouped properly on switchboards. They must be installed inside suitable enclosures, protected from the environment, and located where people can reach them safely when they need to. Nothing should be buried, hidden, or exposed to harmful conditions. It also says that circuits which affect the reliability of supply need their own clear protection and control. One circuit failing should not automatically shut down other circuits unless there is a good reason. Finally, the clause makes it clear that everything must be installed following ASNZS 3000 and following the instructions from the manufacturer. If the manufacturer says the device must be installed in a certain way, then that is the way it must be installed. No shortcuts, no guessing, and no ignoring the instructions. In this clause, the standard tells us the purpose of Section 2. It sets the minimum requirements for how we select and install switchgear and control gear so the whole installation meets the safety rules in Part 1 of the standard. In short, this clause tells us what this section covers and why it matters for safety. Clause 2.2, Arrangement of electrical installation. Clause 2.2.1, Circuits. Clause 2.2.1.1, General. This clause explains how we should break an installation into circuits. The idea is to create circuits that make sense, are safe, and are easy to manage over the life of the installation. The designer should think about how the equipment works together. Some things need to run in groups, and some things have special needs from the user. The load on each circuit must match the protective devices, so nothing is overloaded. Another key concept is what happens when a circuit fails. If a single circuit trips, we do not want critical equipment to stop, and we want faults to be easy to find. The installation should also let people do maintenance or upgrades without turning off power to everything else. Safety service circuits must be kept separate from normal circuits so safety systems keep working even when something else fails. We usually divide circuits into common groups such as lighting, socket outlets, heating and cooling, motors, control systems, and safety services. This keeps the installation tidy and easy to understand. Clause 2.2.1.2 Origin of submains and final subcircuits. This clause is simple. Every submain and every final subcircuit must start at one switchboard. All the live conductors for that circuit must come from the same place. This keeps circuits clearly identified, easy to isolate, and easy to test. Clause 2.2.1.3 Common neutral. This clause explains when a neutral is needed and how common neutrals can be used safely. Any circuit that needs a neutral for the equipment must include one. Sometimes one neutral can serve more than one circuit, but only if all those circuits come from the same supply and if certain safety rules are met. The common neutral must stay continuous and must not rely on the terminals of switches or equipment. If a final subcircuit shares a neutral, the actives and the neutral must be controlled together using linked devices. The neutral must be clearly marked at the switchboard so people know exactly which actives it belongs to. If an appliance can be supplied from more than one source, all those supplies must have one common isolating switch. This prevents confusion and makes sure the entire appliance can be made safe during work. The clause also reminds us that common neutrals can rise to dangerous voltage if they are disconnected while active conductors from different circuits are still connected, so the design must avoid that situation. The neutral must have enough current carrying capacity to match the associated active conductors. Clause 2.2.1.4 Electric vehicle charging circuits. This clause points us to the appendix for extra rules about electric vehicle charging. In New Zealand, only circuits that directly supply electric vehicle chargers must follow those extra requirements described later in Clause 7.9. Clause 2.2.2 Maximum demand. This clause explains how to work out the maximum demand of the installation. The idea is that the supply to consumer mains, submains, and final subcircuits must be large enough for the way the installation is laid out and the way the equipment will actually be used. Maximum demand can be worked out in a few different ways, depending on the job. If the real, measured demand ends up higher than the calculated value, then the measured value becomes the true maximum demand. One way to work it out is by calculation. The standard gives guidance on how to calculate maximum demand for different types of installations. The important idea is that different places use electricity differently, so calculations can vary. Another way is by assessment. This is used when the loads are unpredictable, or when the installation is large or complex, or when the building has a special type of use. In these cases, experience and professional judgment may give a better picture of the maximum demand. Another option is measurement. This means recording the highest rate of electricity use over a 30-minute period using a demand meter. This gives a real number based on how the installation actually behaves under load. Another method is limitation. Here, the maximum demand is limited by the rating of a fixed circuit breaker, or by the load setting of an adjustable circuit breaker. For consumer mains and submains, the maximum demand is the sum of the current settings of the devices protecting the final subcircuits and any extra submains. The key idea is that the method chosen must give a realistic and safe value for the installation. Clause 2.2.3 Selection and installation of conductors. This clause simply points us to Section 3, which explains how conductors must be chosen and installed. The idea is that conductor selection always follows the rules in Section 3 of ASNZS 3000. Clause 2.2.4 Operating characteristics of equipment. Clause 2.2.4.1 General. This clause explains that every item of electrical equipment must be selected and installed so it meets the requirements of this section and any other relevant parts of the standard. If a device performs more than one function, each function must meet the rules that apply to it. The idea is that equipment must be suitable and safe for how it is used, not just for what it is labeled as. Clause 2.2.4.2 Voltage. This clause says the equipment must match the nominal voltage of the circuit it is connected to. In simple terms, the voltage rating of the equipment must be correct for the supply. Clause 2.2.4.3 Current. This clause says equipment must be able to handle the normal current of the circuit, including any effects from inductive or capacitive loads or from harmonics. It must also be able to cope with abnormal currents for as long as the protective device allows during faults. The idea is that the equipment should not be damaged during either normal use or expected fault conditions. Clause 2.2.4.4 Frequency. If frequency affects the performance of the equipment, the rated frequency must match the supply frequency. In most cases, this means the equipment must suit 50 Hz. Clause 2.2.4.5 Power. This clause says that the power rating of the equipment must be suitable for the duty it needs to perform. The idea is simple: the equipment must be able to deliver the power required without overheating or failing. Clause 2.2.4.6 Effects on operator or other equipment. This clause explains that the equipment must not cause harm to people or create problems for other equipment when it is used normally. It must not interfere with the supply, and it must not cause dangerous conditions during switching. The note reminds us that some equipment requires trained operators, and this may limit where such equipment can be used. Clause 2.3 Control of electrical installation. Clause 2.3.1 General. This clause explains that every installation must have devices that allow us to prevent or remove hazards. These devices make it safe to operate, repair, and maintain electrically powered equipment. They are extra safety measures, and they work together with the protective devices described later in the standard. The installation must have switching and disconnection devices so that anyone doing work can make the equipment safe. Any device we use for this purpose must be chosen to match the function it needs to perform. The standard groups these functions into four main types. Isolation is the function that fully separates the equipment from the supply. Emergency switching is for situations where the supply must be cut off quickly to remove danger. Mechanical maintenance switching makes equipment safe for physical work. Functional control is everyday switching used to run equipment. If one device performs more than one of these functions, it must still meet the rules for each function it performs. Clause 2.3.2 Common Control Requirements. Clause 2.3.2.1 General. This clause explains that every circuit must be capable of being isolated from all of its supply conductors. Depending on the system, this may be done by isolating all conductors or by isolating only the conductors that must be disconnected for safety. Where the conditions are suitable, a group of circuits may be isolated by one common switch. This helps when circuits work together or feed one piece of equipment. Any means of isolation must make sure the equipment cannot become live by accident. The isolation device must need a deliberate action to re-energize the equipment. Extra precautions may be used, such as fitted padlocks, warning tags, lockable spaces, or short-term earthing. These measures help prevent someone from accidentally switching the supply back on. If equipment contains live parts from more than one supply, there must be clear notices warning people that different supplies exist. These warnings help anyone working on the equipment identify which circuits must be isolated. The only exception is when an interlocking arrangement guarantees that all circuits are isolated, or when the live parts are safely covered so accidental contact is not possible. Where needed, the installation must also provide a way to discharge stored electrical energy before work is carried out. Clause 2.3.2.1.2 Alternating Current Systems. This clause explains how isolation works in an AC system. All active conductors in an AC circuit must be able to be isolated by a device designed for isolation. For neutral conductors, the rules depend on how the system is arranged. Normally, we do not isolate the neutral conductor of a consumer main, or a neutral that is also used as a combined protective earthing and neutral conductor. But there are some cases where the neutral may be switched, such as a multi-pole device that switches all poles together, or a device that ensures the neutral cannot remain open when the actives are closed. If a switchboard needs to disconnect all live conductors of a circuit, the device must be designed so the neutral cannot be disconnected or reconnected without the actives being disconnected first and reconnected last. This protects people from unsafe neutral conditions. The safe sequence is simple: disconnect the actives first, then the neutrals. Reconnect the neutrals first, then the actives. Fire pump control circuits follow a special rule which requires the neutral to be switched. And fuses must never be installed in the neutral in accordance with ASNZS 7.5.6.4. An earthing conductor must never be isolated or switched. A combined PEN conductor must also never be isolated or switched. Clause 2.3.2.1.3 Direct current systems. In ADC system, all conductors must be capable of being isolated. The standard points to extra guidance for DC isolation in the appendix. Clause 2.3.2.2 Devices for isolation. Clause 2.3.2.2.1 General. This clause explains what an isolation device must be able to do. A device for isolation must be able to disconnect all active conductors of that circuit. A semiconductor device cannot be used by itself for isolation because it cannot guarantee a safe open state. The isolation device must be able to withstand any impulse voltage that could appear at the point of installation. It must not trick the user into thinking it is off when it is actually on. It must clearly show when the isolating contacts are open. The symbols O for off and I for on are considered acceptable ways to show this. The device must be installed so it cannot operate accidentally, even if hit or knocked. It must be able to disconnect all live conductors of the relevant supply and must be easy to reach. If the device cannot interrupt normal load current, extra measures must prevent it from being operated while load is still flowing. This may include interlocking with a circuit breaker or using warning notices. When the isolation device is a switch, it must be able to stay in the open position. Isolation may be achieved by several types of equipment, including switch disconnectors, multi-pole or single-pole disconnectors, plugs and socket outlets, fuses, links, or special terminals that do not need the conductor removed. Clause 2.3.2.2.2 Identification. This clause explains that all isolation devices must be clearly identified so people know which circuit or equipment they isolate. Identification can be by marking or, when isolating one item, by placing the device where it is obvious. A switch that displays the recognized isolation symbol from the relevant product standard is considered suitable for isolation. The standard also lists the product standards that apply to isolation devices. Clause 2.3.3 Main switches. Clause 2.3.3.1 Introduction. This clause explains the purpose of main switches. A main switch must let people isolate the electricity supply quickly and safely. That includes ordinary users, electrical workers, and emergency services. The idea is that if something goes wrong, or if urgent work is needed, the whole supply or part of the installation can be turned off immediately. Main switches must also allow safety services to keep running during an emergency. The supply to emergency equipment must not be cut off unless absolutely necessary. Clause 2.3.3.2 General. This clause says that every electrical installation must have a main switch, located on the main switchboard, that controls the entire installation. If the installation has more than one supply, then each supply must have its own main switch on the main switchboard. There is an exception for alternative supplies such as generators or solar systems. Those main switches can be located on another switchboard, as long as they meet the product standard that applies to that kind of supply. Any part of the installation that supplies safety services needs its own main switch, separate from the switch that controls the normal installation. This ensures emergency equipment can be kept running when everything else is turned off. Every main switch must meet the same rules as any isolation device. It must be easy to operate, reliable, and clearly identified. The standard also gives a list of equipment that does not need to be controlled by a main switch. This includes consumer mains, metering equipment, certain control systems, voltage sensing equipment, fault current limiters, and surge diverters. These items are normally placed on the supply side of the main switch for safety or operational reasons. Clause 2.3.3.3 Number of main switches. This clause says the number of main switches must be kept as low as possible, because too many switches can make emergency control confusing. Domestic installations must have only one main switch for each separately metered supply, or for each separately controlled portion of the building. If a house contains more than one independent dwelling, each dwelling must have its own main switch. Clause 2.3.3.4 Location and operation. Main switches must be placed where people can reach them easily in an emergency. They must not be mounted too high. The operating handle must be no more than 2 meters above the floor or any safe platform nearby. There is one exception. A main switch does not need to be accessible if the switchboard is on public land and the installation is protected by other safety measures. Examples include telephone cabinets, traffic control equipment, or bus shelters. The operating handle for a main switch must be simple and mechanical. It must use a handle, lever, or push button that gives a clear and solid action. Electronic screens or touch panels cannot be used as the primary means of operating a main switch. They may be used only for remote control, as long as a physical mechanical operator still exists. If a building has more than one occupier, each occupier must have an isolating switch that disconnects only their portion of the installation. The switch must be easy to access from their entrance, and it must meet the same main switch requirements. Clause 2.3.3.5 Identification. A main switch must be clearly marked with the words main switch. It must stand out from the other devices on the switchboard so that anyone can identify it quickly in an emergency. If a switchboard has more than one main switch, each one must show which part of the installation it controls. If operating a main switch turns on or isolates an alternative supply, a notice must clearly show the location of the correct main switch for that supply. Where an installation has multiple supply points, such as a building with more than one incoming feed, each main switchboard must have a notice showing where the other supplies and switchboards are located. Supplementary or alternative supplies must have main switches labeled to show the energy source. Clause 2.3.3.6 Remote control. This clause explains how remote control of main switches must be done. Any remote control equipment must be clearly identified and must be located in a place suited to how the installation operates. When a remote control device is used, activating it must cause the main switch to isolate the supply to the parts of the installation that need to be disconnected. If the remote system also allows the main switch to be closed again, then extra precautions must be taken. The design must prevent the switch from closing by accident due to a control fault. There must be a way to lock the main switch in the open position. The remote system must not allow the main switch to be overridden or bypassed. Where remote control is used for a general installation, it does not need to be provided separately for safety services. Safety service switches must follow the rules in Clause 7.2. If an electronic touch screen or programmable control system is used for remote control, the main switch must still meet the mechanical operating rules listed earlier. Clause 2.3.4 Additional isolating switches. Clause 2.3.4.1 Electrical installation in an outbuilding. This clause explains when an outbuilding needs to be treated as its own electrical installation. If the outbuilding has a maximum demand of 100 amps or more per phase, and it has its own switchboard, then it must be treated as a separate installation. This means it will need its own isolating switches and its own main switch arrangements. For main switches in an outbuilding, The rule is that the main switch or isolating switch must be installed on the switchboard inside the outbuilding. This gives anyone working in the outbuilding a safe way to isolate the supply without going back to the main building. If the outbuilding is supplied by more than one submain, each submain must have its own main switch. Those switches do not need to be mounted side by side, but there must be a clear notice showing where all the other main switches for that outbuilding are located. This helps anyone working in the outbuilding isolate every supply safely. Clause 2.3.4.2 Submains and final subcircuits greater than 100 amps. If a submain or a final subcircuit has a rating above 100 amps per phase, then it must have its own isolating switch at the switchboard where the circuit starts. This isolating switch must control that circuit only. There is an exception. If fault current limiters or fuses protect small submains that branch off large rising mains, such as in multi-story buildings, the separate isolating switch is not required. Clause 2.3.4.3 Alternative supply. This clause explains that if the installation has an alternative supply, such as a generator or another source installed under Clause 7.3, then an isolating switch must be provided either at the supply source or at a suitable switchboard. This ensures the alternative supply can be safely controlled and isolated. Clause 2.3.4.4 Identification. Any isolating switch required under this clause must be clearly marked so people know which circuits it isolates. Where the isolating device cannot be placed near the equipment it controls, a suitable warning notice must be fixed on the board or enclosure to tell people where the isolator is located. If a switch automatically connects an alternative supply when operated, it must be marked to show its purpose clearly. Clause 2.3.4.5 Appliances and accessories. This clause reminds us that appliances and accessories, including motors, must have proper isolation and switching devices. These devices must follow the rules in the relevant sections of the standard, especially Section 4 and Section 7. Clause 2.3.5 Emergency switching including emergency stopping. Clause 2.3.5.1 General. This clause explains that emergency switching must be provided wherever it might be necessary to quickly control the electricity supply to remove a danger. Emergency switching might be needed to switch off equipment, or in some cases to switch equipment on, depending on how the danger is removed. The emergency switching device must be an isolating device when there is a risk of electric shock. The design of the emergency switching arrangement must not create extra danger or interfere with safely removing the original hazard. The standard gives examples of places where emergency switching is important. This includes machinery, conveyors, groups of machines, pumping systems for flammable liquids, ventilation systems, large buildings, research facilities, boiler rooms, large kitchens and teaching laboratories. Clause 2.3.5.2 Emergency switching devices. An emergency switching device must be able to remove the hazard quickly. It may be a single device that interrupts the incoming supply, or a combination of devices that act together by a single action. The device must be able to break the full load current of the equipment, including stalled motor current where needed. If the device is manually operated, it must interrupt the main circuit directly. If it is operated by a remote control system, it must open when the control coil loses power or another reliable method is used. The device must have a way to latch or hold the switch in the off or stop position, so it cannot restart accidentally. It must not re-energize the equipment automatically. If there is likely to be danger when the equipment restarts, the device must require a manual reset before power can be restored. Plugs and socket outlets must not be used as emergency switching devices. There is one exception. If equipment is supplied from a socket outlet that has its own switch, then that switch may be used for emergency switching. Clause 2.3.5.3 Installation. Emergency switching devices must be installed where they are easy to reach in an emergency. They must be placed so that anyone can operate them quickly if danger occurs. If remote operation is needed, the remote position must also be obvious and easy to reach. Clause 2.3.5.4 Identification. Devices used for emergency switching must be clearly marked so people can recognize them instantly. Handles, levers, or push buttons must be permanently identified and must be colored red with a contrasting background. There is an exception. If a lanyard, chain, or rope is used for remote operation of an emergency stop device, such as above a conveyor, it does not need to be colored red. Clause 2.3.6, Shutting down for mechanical maintenance. Clause 2.3.6.1, General. This clause explains that when electrical equipment has moving parts, heat, or anything that can cause physical injury, we must have a safe way to shut down the supply before doing mechanical maintenance. The danger might come from rotating machinery, conveyors, motors, heating elements, or unexpected mechanical movement. The main idea is simple. Before anyone works on equipment that moves or creates heat, the electricity must be shut off in a way that prevents the equipment from starting unexpectedly. Because of this, the switch used to shut down the supply must be arranged so it cannot be bumped, knocked, or vibrated back into the on position. Locking devices, warning notices, or a lockable enclosure may be used to prevent accidental reconnection. However, if the person doing the maintenance keeps full control of the shutdown switch at all times, then locking facilities are not required. Clause 2.3.6.2, Devices for shutting down. Devices used for shutting down during mechanical maintenance must work by manual operation. They must clearly show when they are in the off position. They must also be designed so they cannot switch back on by accident due to impact or vibration. These devices only need to interrupt the main live conductor that powers the mechanical movement. They do not need to disconnect every conductor. In some cases, the control circuit of a drive may be interrupted instead, but this is only allowed if other safeguards, such as mechanical restraints, prevent movement. If the shutdown switch is located away from the equipment it controls, then it must have a way to be locked in the open position so the equipment cannot restart while someone is working on it. Clause 2.3.6.3, Installation. The device used for shutting down must be installed in the main circuit so it properly removes the supply to the mechanical parts. It must be positioned so that the relevant conductor is safely interrupted. Clause 2.3.6.4, Identification. Any device used for shutting down during mechanical maintenance must be marked clearly so that workers know exactly what it isolates. It must be easy to find and convenient to use in a maintenance situation. Clause 2.3.7, Functional Control Switching. Clause 2.3.7.1, General. This clause explains functional switching. Functional switching is everyday operational control, turning equipment on or off for normal use, not for safety. Examples include switches, contactors, and solid-state devices used to start or stop equipment as part of regular operation. Each part of a circuit that needs to be controlled separately must have its own functional switching device. A single functional switch can operate several pieces of equipment together if they are intended to run at the same time. Sometimes the switching device may be built into the equipment itself. Clause 2.3.7.2, Functional Switching Devices. Functional switching devices must be suitable for the heaviest duty they are expected to perform. This includes how often they operate, how much current they carry, and any stresses such as motor loads or lamps with low power factor. Disconnectors, fuses, and links must not be used for functional switching. The device must be properly designed for switching duty. Devices that control low power factor loads, such as motors or fluorescent lighting, must follow the correct rating rules unless the switch is specifically designed for that purpose. For example, some switches are designed under the AC23A category and do not need further derating. Functional switching devices do not need to show the on and off positions, except for appliance switches, which must show the off position. Clause 2.3.7.3, Identification. Functional switching devices normally do not need markings for on or off. The exception is switches on appliances, which must show the off position. Clause 2.3.7.4, Control Circuits. Control circuits must be designed and protected so that a fault in the control wiring does not cause dangerous operation of the connected equipment. This includes preventing sudden or unexpected starts due to wiring faults or interference between control circuits and other conductors. The main idea is that control circuits must not create a situation where machinery operates unpredictably. Clause 2.4, Fault Protection. Clause 2.4.1, General. This clause explains the recognized methods of protecting people from electric shock caused by a fault. A fault means a dangerous connection between a live part and something that should not be live, such as exposed metalwork. The standard recognizes three main ways to provide fault protection. The first way is automatic disconnection of supply, which is the most common method. The second way is using Class II equipment or equivalent insulation, which provides extra insulation so no exposed metal becomes live. The third way is electrical separation, where one circuit is fully separated from others so a fault cannot produce a dangerous voltage. The standard then explains that the detailed rules for automatic disconnection of supply are found in later clauses. Clause 2.4.2, Protection by automatic disconnection of supply. This clause explains the purpose of automatic disconnection. The idea is to limit the touch voltage during a fault. If a live conductor touches an exposed conductive part, the voltage on that metal must be removed quickly enough to prevent electric shock. To achieve this, two things must happen. First, the exposed conductive parts must be connected to a protective earthing system that meets the rules of Section 5. Second, an overcurrent device or an RCD must disconnect the fault fast enough to keep the touch voltage safe. The combination of proper earthing and fast disconnection is what makes this method effective. Clause 2.4.3, Types of devices. This clause explains which protective devices can be used for automatic disconnection. Any device used must not automatically reclose after it trips. It must stay open until someone resets it safely. The standard lists several types of acceptable devices. These include enclosed fuse links that meet the correct standard, miniature circuit breakers, molded case circuit breakers, and fixed setting RCDs that meet their relevant standards. Other devices without auto-reclose may also be used if they have similar protection characteristics. Semi-enclosed rewirable fuses must not be used for automatic disconnection because they do not reliably clear faults in the required time. There is one exception. Some devices with auto-reclose may be used if they automatically test the insulation before reclosing, and only reclose when the insulation is safe. Clause 2.4.4, Auto-reclose devices. This clause explains when auto-reclose devices are allowed. An auto-reclose device may be used if several important conditions are met. First, it must not be used as the main method of fault protection required by Clause 1.5.6. Second, the auto-reclose must not operate after someone has manually switched the device off. This prevents unexpected reconnection while someone is working. A warning notice must be fixed near the device to tell workers that an auto-reclose function is present. It must also warn them to turn the device off manually and isolate the supply before starting work. There must be a time delay before the first reclose, such as 3 minutes, to reduce the chance of reconnecting during a dangerous condition. The number of reclose attempts must be limited, such as 3 attempts. There is an exception. If the auto-reclose device performs an automatic insulation test and only reconnects when the insulation is safe, then some of these restrictions do not apply. Clause 2.5, Protection against overcurrent. Clause 2.5.1, General. This clause explains that every active conductor must be protected by a device that automatically disconnects the supply whenever the current becomes too high. Overcurrent can be dangerous because it overheats cables and equipment, and the heat or stress can damage insulation or start a fire. The device must disconnect the circuit before the current grows large enough, or lasts long enough, to cause injury or damage. A fuse must never be placed in the neutral conductor. If a device switches the neutral as part of a multi-pole unit, it must follow the isolation rules in Clause 2.3.2.1.2. Protection against overcurrent includes two parts. The first part is protection against overload, which means too much current flowing for too long during normal operation. The second part is protection against short-circuit current, which is a sudden, very high current caused by a fault. Both types of protection must work together, and must match the current carrying capacity of the cables connected to the circuit. The standard also reminds us that the rating of a cable can change depending on how it is installed, the size of the conductor, and its construction. So the protective device must match the actual installation conditions. Clause 2.5.1.2 Consumer Mains. This clause explains how overcurrent protection must be arranged for consumer mains. There are several acceptable options. One option is to place both overload and short-circuit protection at the point of supply. Another option is to provide short-circuit protection at the point of supply, and put overload protection at the main switchboard. A third option allows you to omit short-circuit protection at the point of supply if overload protection is provided at the main switchboard and the consumer mains are designed and installed to meet the construction rules in Clause 3.9.7.1.2. Consumer mains that do not have a service protective device at the point of supply are called unprotected consumer mains. Where unprotected mains are used, the earthing and protection arrangements must follow the diagrams and requirements shown later in the standard. If the consumer mains supply multiple circuits, and each of those circuits already has overload protection, then overload protection at the point of supply is not needed as long as the total load does not exceed the rating of the consumer mains. Clause 2.5.1.3 Submains and final subcircuits. This clause covers overcurrent protection for all subcircuits within the installation. Overload and short-circuit protection must be installed at the origin of every circuit. Protection must also be added at places where the cable becomes smaller or has a reduced current carrying capacity. There are a few exceptions. Some circuits must not be interrupted because the loss of power would create a greater danger than overcurrent itself. These include some safety system supplies, lifting magnets, or certain control circuits. In these situations, the design may require special alarms or monitoring systems instead of disconnecting the supply automatically. Another exception allows protective devices to be placed at a different location when permitted by other clauses in the standard. In some cases, protection may be omitted if allowed by later clauses in Section 2.5.3 or 2.5.4. Clause 2.5.1.4 Omission of protective device for safety reasons. This clause explains that a protective device may be left out when opening the circuit unexpectedly would create a greater danger than leaving the circuit energized. Examples include some control circuits in safety systems or in the secondary circuits of certain transformers. In these cases, a fault alarm or monitoring device is often recommended so that dangerous conditions can still be detected. Clause 2.5.2 Devices for protection against both overload and short-circuit currents. This clause explains the requirements for devices that protect against both overload and short-circuit current. The device must be able to break any overcurrent up to the maximum prospective short-circuit current at the point where the device is installed. It must also meet all the requirements of the overload and short-circuit protection clauses in Section 2.5.3 and Section 2.5.4. The standard allows several types of devices to be used. These include circuit breakers with both overload and short-circuit releases, fuse combination units, and fuses with enclosed fuse links such as high rupturing capacity fuses. A circuit breaker may also be used together with a fuse to provide the required protection. Semi-enclosed rewirable fuses must not be used for this purpose because they cannot reliably interrupt short-circuit currents. General-purpose fuses in most modern circuit breakers normally combine overload and short-circuit protection into one device. A fuse includes all the parts that make up the complete protective unit. Some circuit breakers can replace older fuse carriers, but if they are used in place of semi-enclosed fuse carriers, they must be rated at not more than 80% of the current carrying capacity of the protected conductor. Screw-type enclosed fuses that comply with the correct part of the IEC standard are also acceptable. Clause 2.5.3 Protection against overload current. Clause 2.5.3.1 Coordination between conductors and protective devices. This clause explains how the overload protective device must match the cable it is protecting. For the protection to work properly, two simple conditions must be met. The first condition is that the current the circuit is designed for must not be greater than the continuous current carrying capacity of the conductor. In other words, the expected maximum load on the circuit must be less than or equal to the rating of the cable. The second condition is that the protective device must operate quickly enough to stop the conductor from overheating when an overload occurs. The device must trip before the cable reaches a dangerous temperature. The standard gives formulas to express these relationships, using the design current of the circuit, the rating of the device, and the cable's capacity. The operating current of the device during overload depends on the device type. For circuit breakers, the effective overload operating current is usually 1.45 times the rated current. For fuses, it is normally 1.6 times the rated current, following the International Fuse series. A note explains that a fuse should normally be rated at no more than 90% of the current carrying capacity of the cable it protects. This ensures that the fuse rating and the cable rating stay coordinated. The standard also reminds us that adjustable devices must be set correctly for the load they protect, and that overload protection does not protect against all types of long-duration low-level overheating unless the system is designed with proper limits. Clause 2.5.3.2 Position of overload protective device, general arrangement. This clause explains where overload protection must be placed. Normally, the overload device must be installed at the origin of every circuit and at each point where the cable becomes smaller or its current carrying capacity reduces. There is one general exception. If the conditions in clauses 2.5.3.3 or 2.5.3.4 are met, then the overload device may be placed somewhere else or may be omitted entirely. These exceptions are explained next. Clause 2.5.3.3 Alternative position of overload protective device. This clause describes the conditions where the overload device may be placed somewhere other than the origin of the circuit. The first condition is that the conductor must have no branch circuits or socket outlets between its origin and the location of the protective device. This means there is no chance of supplying extra loads before the protection is reached. The second condition applies when the conductor supplies one or more circuits that are already individually protected against overload. If the sum of the ratings of those downstream devices does not exceed the capacity of the conductor feeding them, then the overload protection can be placed at another suitable location, such as within a switchboard or busway. The standard provides diagrams showing typical examples of these alternative positions. Clause 2.5.3.4 Emission of overload protective device. This clause explains when overload protection may be left out entirely. One situation is when opening the circuit during an overload would create a greater danger than leaving the circuit energized. This applies to certain safety system supplies, lifting magnets, or some machine excitation circuits. Where this happens, an alarm system or monitoring device may be recommended instead of automatic disconnection. Another situation is when the conductor is not in a location where opening the circuit would create a fire or explosion risk, and one of the following conditions is met. The first condition is that the conductor is on the load side of a change in capacity and is already protected by a device placed upstream. The second condition is that the conductor supplies equipment that cannot cause an overload, such as certain heating appliances. The conductor must also have no branches or socket outlets connected along the way. The third condition is when the conductor supplies equipment used only for telecommunications, signaling, or control, where overload currents cannot occur. Examples of these arrangements are shown in later figures of the standard. Clause 2.5.4 Protection against short-circuit current explains how circuits are protected when a fault causes a sudden and very high current to flow. A short circuit is not the same as an overload, because an overload builds up over time, while a short circuit happens instantly and can reach extremely high current levels. If this current is not cleared quickly, conductors can overheat, insulation can break down, and serious damage or fire can occur. This clause explains how to select suitable protective devices and where they must be installed so the installation remains safe. Clause 2.5.4.1, determining the prospective short-circuit current, explains that the prospective short-circuit current must be known at every relevant point in the installation. This value represents the highest fault current that could flow if a short circuit occurred at that location. The value can be obtained either by measurement using suitable test equipment or by calculation. Whichever method is used, the result must be realistic so that protective devices with adequate braking capacity can be selected. Clause 2.5.4.2, characteristics of short-circuit protective devices, explains that the braking capacity of a protective device must be at least equal to the prospective short-circuit current at the point where the device is installed. If the available fault current is greater than the device rating, the device may fail violently instead of providing protection. An exception is allowed where a device with a lower braking capacity is used together with an upstream device that has sufficient capacity. In this case, the devices must be coordinated so that the total energy released during the fault does not exceed what the downstream device and the connected conductors can safely withstand. The explanation also recognizes that other effects, such as mechanical stress, arcing energy, and forces caused by very high currents, may need to be considered, and this information is normally provided by manufacturers. The clause also explains that short-circuit currents must be cleared before a conductor reaches its maximum safe temperature, because excessive heating can damage the conductor or its insulation. For short-circuit durations up to 5 seconds, an approximate relationship is used to confirm that disconnection occurs quickly enough, taking into account the fault duration, the conductor material factor from ASNZS 3008, the conductor cross-sectional area, and the fault current. Notes explain that correct material factors must be used, that very short duration faults are treated differently, and that in some cases a protective device may have a higher rating than the cable, provided the short-circuit energy limit is not exceeded. Clause 2.5.4.3, position of devices for short-circuit protection, explains that, under normal conditions, a short-circuit protective device must be installed at the origin of every circuit and at any point where the conductor size is reduced. This ensures that smaller conductors downstream are protected against high fault currents. The clause also allows for specific exceptions where the device may be installed in a different position or omitted, subject to conditions explained later in the standard. Clause 2.5.4.4, alternative position of short-circuit protective device, explains that in some situations the protective device does not need to be located exactly at the circuit origin. One situation is where the conductor section between the origin and the device is very short, is mechanically protected to reduce the likelihood of a short circuit, and is installed in a way that minimizes fire risk. Another situation allows the device to be located on the supply side of a reduced conductor, provided the operating characteristics of the device still give adequate protection to the conductor downstream. In practice, this is confirmed by checking that the fault energy let through by the device does not exceed what the conductor can safely withstand. Clause 2.5.4.5, omission of short-circuit protection, explains that in special cases, short-circuit protection may be omitted altogether. This is permitted only where automatic disconnection could create a greater danger than the short circuit itself, where consumer mains are installed in accordance with the special rules for unprotected mains, or where conductors connecting generators, transformers, rectifiers, or batteries to their switchboard meet strict installation conditions. In these cases, the wiring must be installed to minimize the risk of short circuit, must avoid locations that increase fire risk, and must still have short-circuit protection provided for the remainder of the circuit at the associated switchboard. Clause 2.5.5, protection against switchboard internal arcing fault currents. Clause 2.5.5.1, general. This clause explains when we must protect switchboards from internal arcing faults. An internal arcing fault is a very dangerous fault that creates extremely high temperatures, pressure, and burning metal. It can seriously damage equipment and put people at risk. Protection must be provided whenever a switchboard is rated at 800 amps or more per phase. This applies whether the switchboard is operating normally or being worked on. The supply conductors feeding into the switchboard must also be arranged to reduce the chance of an arc starting. This can be done by using proper insulation or by separating conductors so that accidental contact is unlikely. The standard then explains that the switchboard must meet at least one of several approaches. The first option is to reduce the chance of an internal fault starting. The second option is to limit the harmful effects if a fault does occur. The third option is to use internal separation within the switchboard to prevent the fault spreading. Clause 2.5.5.2 Reduction of the probability of the initiation of a switchboard internal arcing fault. Switchboards rated at 800 amps or more per phase must be built with internal separation in line with ASNZS 61439.2. Separation is required between the busbars in the functional units, between different functional units, between terminals used for external conductors, and between the general supply section and any safety service section of the switchboard. The purpose of this separation is simple. It prevents tools, loose parts, or accidental contact from causing an arc. It also helps ensure that one fault does not spread into another part of the switchboard. The notes explain that separation can be achieved in several ways, including barriers, insulated covers, or specific construction forms. The main idea is preventing things from touching live parts unintentionally. Clause 2.5.5.3 Limitation of the harmful effects of a switchboard internal arcing fault. If a fault does occur, this clause explains how to limit the damage. A protective device must be installed that will disconnect the arc as quickly as possible. The arcing fault current is normally assumed to be between 30% and 60% of the prospective short-circuit current. To keep the switchboard safe, the protective device must operate at a current below 30% of the prospective short-circuit level. A maximum clearing time is given by a formula. The idea is that the fault must be cleared before it produces more energy than the switchboard can safely withstand. An example in the standard shows how to calculate the clearing time using the current rating of the switchboard and the prospective fault level. Earth fault protective devices must not have settings higher than 1200 amps. This ensures that earth faults contributing to an arcing event are cleared fast enough. The settings of these protective devices must be checked during inspection. The notes explain that discrimination with the electricity distributor's protective devices may be needed, and that arc detectors can be used to speed up response time. Clause 2.5.6 Coordination of overload and short-circuit protective devices. This clause explains how protective devices must work together. A single device may provide both overload and short-circuit protection if it meets all requirements for both functions. If two separate devices are used, their characteristics must be coordinated so that the energy allowed to pass through the short-circuit device does not exceed what the downstream overload device and the conductor can safely handle. These settings must also be verified during inspection. Section 2.5.7 Reliability of supply. Clause 2.5.7.1 General. This part explains that an electrical installation should be arranged so the supply stays as reliable as possible. To do that, the installation is divided into sensible circuits, and the protective devices are chosen so they discriminate properly. That means if a fault happens on one part of the installation, only the device closest to that fault should operate. The rest of the installation should stay energized. The idea is to minimize how much of the supply is lost when a protective device trips. It also explains that the choice of protective devices, and the way they are set, must be checked during inspection in line with Clause 8.2.2, Sub-Clause C, Item 2. Clause 2.5.7.2, Coordination of protective devices. Clause 2.5.7.2.1, General. This clause says that when we choose protective devices, we need to think about two things. One is discrimination, also known as selectivity. The other is backup, also called cascading. Discrimination means that when two or more protective devices are in series, the device downstream should operate for a given fault, and the device upstream should stay closed. In simple terms, the breaker closest to the fault should trip first. The upstream breaker should not trip for that same fault. The goal is to keep the rest of the installation energized. Backup, or cascading, is about how two devices behave when the fault is large, such as a short circuit. It considers how much energy is passed through to the downstream device, and whether that downstream device can withstand that energy safely. It also includes how the two devices share the fault, and how the upstream device helps the downstream one survive high fault currents. The clause reminds us that manufacturer information should always be used where available, because each device has its own curve, its own energy limits, and its own timing behavior. Figure 2.12 in the standard shows the basic idea of discrimination. When the fault occurs on a branch circuit, the protective device for that branch should clear the fault while the upstream protective devices remain intact. That way the supply to the rest of the installation is not interrupted. Clause 2.5.7.2.2, Safety Service Circuit Discrimination. This clause explains that faults in safety service circuits must not cause a loss of supply to the other safety services. A safety service is something that must keep running during an emergency. At the same time, a fault anywhere on the general electrical installation must not interrupt any of the safety services either. The level of fault current considered here goes up to the level of an arcing fault current, which is generally taken as between 30% and 60% of the prospective short-circuit current. To meet this rule, discrimination must be provided between the protective devices so that faults on any one safety service, or faults on the general installation, do not take out the supply to the other safety services. The standard gives an example in Figure 2.13 to show how the devices should be arranged. Clause 2.5.7.2.3, General Supply Circuit Discrimination. For normal circuits, discrimination should be arranged so that if something goes wrong, the loss of supply is as small as possible. That means you coordinate the protective devices on the outgoing circuits with the protective device on the supply side. The coordination is checked using the time current curves for the devices, or using the manufacturer data. For circuit breakers, the downstream protective device is usually labeled C2 and the upstream device C1. The standard explains how to choose settings so that discrimination is maintained. For circuit breakers rated 800 amps or greater, you must use a coordination study with the manufacturer's curves to confirm that discrimination exists. For circuit breakers rated 250 amps up to 800 amps, discrimination is required based on the overload curves, and recommended for the instantaneous and short time delay settings as well. For circuit breakers less than 250 amps, discrimination is generally considered to be achieved when the upstream breaker has a rating at least 1.5 times that of the downstream breaker, as long as both devices have the same curve type. The clause also describes how fuses and circuit breakers can be coordinated. For fuses used together, discrimination is usually achieved when the upstream fuse has a current rating 1.6 times that of the downstream fuse for overload, and at least 2 times for short-circuit currents. For combinations of a fuse and a circuit breaker, the upstream device must be chosen so its curve stays above the overload and instantaneous curves of the downstream device. The standard notes that discrimination requirements mainly apply for switchboards rated at 800 amps or higher. It also reminds designers to use manufacturer data because every protective device behaves differently, especially when short-circuit currents become high or when current-limiting designs are used. These rules help ensure that faults are isolated quickly and safely without shutting down the whole installation. ASNZS 3000 Section 2.6, New Zealand clauses only, additional protection by RCDs. Clause 2.6.1, General. This clause explains why RCDs with a rated residual operating current not more than 30 mA are used as an extra layer of protection. They give added safety in places where earth leakage current might become dangerous, or where people might use equipment carelessly. These RCDs help reduce the risk of electric shock, but they do not replace the main protection required by Clause 2.4. They do not protect against faults between live conductors. They also do not protect against dangerous voltages that may come into the installation from the supply neutral. The idea is simple. RCDs provide additional protection. They trip when an earth leakage current reaches a set level, and this reduces the chance of serious shock. But they are never the only protection. They work together with the other safety measures in the standard. RCDs used for this purpose must have a sensitivity not exceeding 30 mA. Some RCDs are 10 mA, and these give even greater protection. Clause 2.6.2 Selection and arrangement of devices. Clause 2.6.2.1 General. Any RCD used for additional protection must be able to interrupt a circuit when earth leakage rises above its designed trip level. The load rating of the RCD must be at least the same as the maximum demand of the part of the installation it protects, or the highest rating of any overload device on that same part of the installation. Earth or bonding conductors must never pass through the magnetic core of the RCD, because this would affect the correct operation. Circuits must be arranged so the normal leakage from connected equipment will not cause nuisance tripping. We aim to keep normal leakage well below the RCD's rating. Clause 2.6.2.2 Types of RCD. RCDs used in electrical installations must be fixed setting devices that comply with ASNZS 3190, ASNZS 61008.1, ASNZS 61009.1, or IEC 62423. There are several common types. Type AC trips on normal sinusoidal AC leakage. Type A trips on both AC and pulsating DC leakage and is recommended as the general-purpose type for most installations. Type I protects against AC leakage and 10 mA residual currents with fast disconnection. These are used for special locations such as medical areas. Type F protects circuits that may have high-frequency leakage or fast-rising currents, such as from electronic equipment. Type B trips on AC leakage, pulsating DC leakage, and smooth DC leakage from rectifiers or converters. These different types exist because modern equipment can create different leakage waveforms, and the RCD must be designed to detect them correctly. Clause 2.6.2.2.3 New Zealand only. In New Zealand, RCDs required by the standard must interrupt all live conductors. This includes active and neutral conductors. If the RCD is a Type A device, it must meet the New Zealand requirements in ASNZS 61008.1 or ASNZS 61009.1. Clause 2.6.2.3 Protection against initiation of fire. Type S RCDs with rated residual currents from 100 mA to 300 mA may be used to reduce the risk of fire caused by leakage across damaged insulation. They operate more slowly and provide a different kind of protection but are not a substitute for the 30 mA devices needed for shock protection. Clause 2.6.2.4 Arrangement. When additional protection is required for final subcircuits, the RCDs must be arranged to minimize inconvenience and avoid losing supply to large parts of the installation. In any installation where there is more than one RCD and more than one lighting circuit, the lighting circuits must be shared between RCDs so only part of the lighting is lost if one device trips. For residential installations, no more than 3 final subcircuits may be on one RCD. If there is more than one final subcircuit, at least 2 RCDs must be installed. These rules make sure that one tripping device does not shut down the entire home or building. Clause 2.6.3 Additional protection by RCDs. This clause explains when we must install RCDs to give extra protection against electric shock. In simple terms, the rule says that this extra protection sits on top of the normal protection. It does not replace the basic protection, and it does not replace the fault protection that we already need from Clause 2.4. The standard reminds us that other New Zealand standards also talk about RCD requirements, but for our audiobook we focus only on what applies in New Zealand electrical installations under ASNZS 3000. The big idea is this. Extra protection by an RCD is needed in places where a single fault, or people using equipment carelessly, could create a higher risk of electric shock. An RCD that trips at 30 mA, or in some cases 10 mA, brings that extra layer of safety. RCD protection does not fix everything. It cannot protect against faults between live conductors, and it does not protect against dangerous voltages that might enter the installation through the supply neutral. So we still need all the other protective measures required by Clause 2.4. When a fault to earth happens, the RCD must automatically disconnect the supply at a level of earth leakage current that has been set beforehand. That is the essential purpose of additional protection. Clause 2.6.3.3, Installation Requirements, New Zealand only. This clause explains when New Zealand installations must have an RCD for extra protection. For residential installations, extra protection by an RCD with a maximum residual current of 30 mA must be provided for final subcircuits that supply one or more socket outlets, or one or more lighting points, or directly connected handheld equipment such as hairdryers or tools. This also includes combination fan and light units, smoke alarms, bathroom exhaust fans, and ceiling sweep fans, because these are all treated as lighting points. The rule applies across individual domestic installations, residential areas of other electrical installations, multiple residential buildings, and shared external lighting areas. Where RCD protection is required, the device must be fitted at the switchboard where the final subcircuit originates. There are a few exceptions. If a different method of protection is already used that will automatically disconnect the supply under a fault, such as separated supply or extra low voltage, then an RCD might not be required. Another exception applies when a socket outlet is supplying a fixed cooking appliance such as a range or oven or hot plate unit. In those cases, the socket outlet must be placed where it is not likely to be accessed by the general public, and it must be clearly marked to show its restricted use. Clause 2.6.3.3.2, Non-residential installations, New Zealand only. In non-residential installations, 30 mA RCD protection must be provided for socket outlets rated not more than 30 A in education and childcare facilities, including kindergartens, daycare centers, and schools up to Year 13, as well as tertiary or vocational training areas. The purpose is to protect children and young people who may not recognize shock hazards. For junior education and childcare facilities, an RCD with a maximum rated residual current of 10 mA must be used for socket outlets in areas where teaching or caring for children takes place. These RCDs do not need to be Type A unless required for medical devices. Other locations also need RCD protection where socket outlets are used for handheld equipment. This includes outdoor areas, unsupervised public places, and amusement arcades. Some situations are exempt. If another method of fault protection is already used, such as separated supply or extra low voltage, an RCD may not be needed. Another exemption applies in places where disconnecting the circuit by an RCD would cause a danger greater than the leakage current risk, such as some traffic signal circuits. There are also exemptions for mining sites using reduced low voltage. Clause 2.6.3.3.3, Home care installations, New Zealand only. Where medical electrical equipment is installed in home care situations, some devices must be protected by a Type I RCD with a maximum rated residual current of 10 mA, and with a faster tripping time. These installations follow the medical standard as ASNZS 3003. Clause 2.6.3.3.4, Additions and alterations, New Zealand only. When circuit protection on an existing switchboard is replaced, additional RCD protection must be added to the final subcircuit supplied from that switchboard. If socket outlets are added to an existing circuit, and RCD protection is required, the RCD should ideally be installed at the start of the subcircuit, but it may also be installed at the beginning of the new wiring only. Any new RCDs must be recorded at the switchboard. There are two small exceptions. If a socket outlet that is not RCD protected is simply replaced with the same type, the rule does not apply. And if socket outlets are added under an exemption that already applies in Clause 2.6.3.3.1 or Clause 2.6.3.3.2, then extra RCD protection is not required. Clause 2.7, Protection against overvoltage. Clause 2.7.1, General. When we talk about protection against overvoltage, We are talking about keeping people and property safe if the voltage in the installation suddenly rises above what the system is designed for. This can happen for a few different reasons. A fault could happen between a low voltage circuit and a higher voltage circuit. Switching operations can create sudden spikes. Lightning can also cause dangerous voltage surges, especially in areas where lightning is common. Resonant effects in the network can also push the voltage higher than expected. The idea is simple. Where high voltage could cause danger, we must provide suitable protection so the installation stays safe. Clause 2.7.2, Protection by insulation or separation. This clause is about stopping dangerous voltages from getting into other parts of the installation when two circuits of different voltages sit close to each other. The protection can be achieved by using strong insulation, by screening, or by separating the circuits far enough apart so they can't affect each other. For conductors, we use proper insulation screening or physical segregation so a fault can't easily jump across. For transformers, we use similar ideas, strong insulation between windings, or a conductive screen that is earthed, so any fault energy is safely carried away and the supply disconnects if needed. Transformer windings that operate at different voltages must be clearly separated. If a fault does occur inside a transformer, the design must make sure that the protective device will disconnect the supply quickly. Clause 2.7.3, Protection by protective devices. Sometimes we use protective devices to control overvoltage. These devices limit the sudden voltage rise to a level that the installation can safely handle. They must operate fast enough to keep the voltage below the insulation strength of the equipment. They also need to be suitable for the highest voltage that could appear in normal operation, and must not create danger during operation. This standard does not force you to install surge protection devices for lightning. If lightning is a significant risk in your area, another standard explains how to decide on proper lightning protection and which devices to use. Clause 2.8. Protection against undervoltage. Clause 2.8.1 General. Now we move to undervoltage protection. Undervoltage means the supply drops too low, or the voltage is lost and then comes back. Both situations can be dangerous. If the voltage disappears and then suddenly returns, some equipment can start unexpectedly. Imagine a guillotine, a press, or a powered gate suddenly coming back to life. If the voltage drops too low, motors may struggle to start or run, which can cause overheating or even failure. So we provide undervoltage protection when low voltage could create danger for people or property. But if the equipment can safely handle a short interruption without danger, then undervoltage protection is not required. Clause 2.8.2 Selection of protective device. The protective device used for undervoltage must suit the equipment it is protecting. It must follow the requirements and the relevant standards for starting motors and running electrical equipment. If switching the device back on could be dangerous, it must not automatically reclose. For example, if the supply drops out and comes back, we do not want a dangerous machine restarting by itself unless it is designed for safe automatic restart. Instant disconnection by the undervoltage device must not be slowed down by mechanical delays in its contacts. There is one exception. If a short loss of voltage is not dangerous for the equipment, the undervoltage device can be allowed to delay its operation. Undervoltage protection is often provided by special relays or releases that open a switch or breaker when the voltage drops. Non-latched contactors are also used in many installations, because they drop out naturally when voltage is too low. Clause 2.9. Protection against fire hazard due to arcing faults. Clause 2.9.1 General. In this part of ASNZS 3000, we talk about arcing faults and the fire risk they create. An arcing fault is when electricity jumps across a damaged or loose connection. It creates heat, sparks, and can easily start a fire inside a wall, a socket, or a cable. Arc fault detection devices, spoken as AFDDs, are designed to detect this kind of fault early and disconnect the supply before a fire can start. They are protection for final subcircuits, especially in places where a fire would be very dangerous. Common places where AFDDs are useful include any area where people sleep, places where flammable materials are stored or processed, buildings made from combustible materials such as timber, and any structure where fire can spread quickly. The standard explains that AFDDs are an extra layer of safety. They do not replace other protective requirements. Clause 2.9.2 Type. Any AFDD used in an installation must comply with standard IEC 62606. This ensures the device can correctly detect and disconnect arcing faults. Clause 2.9.3 Rating. The AFDD must have a load current rating that is at least equal to the circuit protective device it works with. In other words, it must be sized so it can safely operate on that circuit. Clause 2.9.4 Arrangement. The AFDD must be installed at the switchboard where the final sub-circuit begins. This gives full protection for the entire circuit. Clause 2.9.5 Alterations. When you alter an existing installation, especially old wiring that may be damaged or weakened, you should consider installing an AFDD for extra protection. Things like vermin damage, aged insulation, or brittle wiring can increase the chance of an arcing fault, so adding an AFDD can help reduce the fire risk. Clause 2.9.6 Final subcircuits in Australia. This part is not applicable to New Zealand because Australia does not require AFDD installation. For New Zealand, use the next clause. Clause 2.9.7 Final subcircuits in New Zealand. In New Zealand, AFDD protection is required for any final subcircuit rated at 20 amps or less when it supplies locations with a higher fire risk. These include places where flammable or combustible materials are processed or stored, such as farm sheds, woodworking shops or storage areas, places containing irreplaceable items, historic buildings built from flammable materials, and school dormitories where socket outlets supply student areas. In these locations, wiring faults can lead to fire, so the standard requires an AFDD to be installed at the switchboard that feeds these subcircuits. The notes explain that if the wiring is in poor condition, such as circuits passing through high-risk areas, AFDD protection is strongly advised even if it is not strictly required. Section 2.10 Switchboards. Clause 2.10 begins by telling us the basic idea of a switchboard. A switchboard is the place where we mount and enclose the switchgear and the protective devices for the installation. In simple terms, this is the control center of the electrical system. Clause 2.10.1 explains the general requirement. Every installation needs a switchboard, or sometimes more than one, so that we have a safe and organized location for the main switches, the protective devices, and any other necessary control equipment. The standard also reminds us that a main switchboard must be provided for every electrical installation. This is the switchboard that contains the main switch or switches, and the main protective devices. In some rare cases, the main switch does not need to be located directly on the main switchboard, but it still has to be close enough to be safely reached and operated when needed. Clause 2.10.2 covers the location of switchboards. Switchboards need to be placed in suitable, well-ventilated areas. They must be protected from moisture and must be arranged so that electricians can safely install, replace, or maintain equipment inside the board. That means there must be enough room in front of the board, and enough space for tools and hands to work safely. The access requirements continue with the idea that people must be able to safely reach and operate the equipment. The standard says there must be a clear space in front of the switchboard to allow safe operation and adjustment. For normal installations, this space is at least 1 meter from the face of the board. In a domestic installation, this can be reduced to 0.6 meters from the front. Around switchboard doors, we need at least 0.6 meters of clear space so the doors can open and close safely. No one should be forced into the switchboard or trapped by a door. This is especially important when the doors open into passageways or narrow walkways. The script continues with the requirement for safe exit paths. If a fault happens at the switchboard, people must be able to move away quickly without being blocked by equipment, shelves, or obstacles. This is why exit pathways around switchboards must be clear. Clause 2.10.2.3 explains the requirements for locating the main switchboard. It must be readily accessible. In multiple building sites or multiple tenancy buildings, the main switchboard must not be hidden inside a single tenant's area. It has to be in a location where authorized people can reach it easily and quickly. Clause 2.10.2.4 explains identification of main switchboard. The main switchboard must also be permanently marked with the words main switchboard. The label must be clear, easy to read, and made of durable material. If the room or enclosure itself is the main switchboard room, that room must also be clearly marked, unless the installation is a small domestic one where the location is obvious. Clause 2.10.2.5 covers restricted locations. There are several places where switchboards cannot be installed. For example, a switchboard cannot be installed less than 1.2 meters above the ground unless special conditions are met. A switchboard cannot be installed above water containers or above cooking appliances unless it is fully enclosed and protected from splashing. A switchboard inside a cupboard must be placed in its own dedicated section of the cupboard, with nothing else stored in that space. The cupboard doors must allow safe operation and safe maintenance. The standard also warns against installing switchboards near swimming pools, spas, or in any damp situation zone because of the higher risk of electric shock. Switchboards must not be installed inside a sauna, inside refrigeration rooms, inside fire-isolated stairways, or in areas classified for hose-down sanitizing unless the degree of protection is appropriate. Switchboards must not be installed in the path of fire exits because smoke from a switchboard fault can block escape routes. If a switchboard is placed inside a cabinet or compartment, the doors must be sealed to stop smoke escaping into the escape path. The standard also restricts installations near fire sprinklers. A switchboard cannot be placed where a sprinkler head could spray water onto it, unless the switchboard has protection to at least IPX4, or a shield is provided, or deflectors are fitted to the sprinkler heads. Finally, the standard covers hazardous areas. A switchboard must not be placed in a hazardous area, such as an area with flammable gas or vapor, unless the switchboard is specifically designed and certified for installation in that hazardous zone. This completes the spoken explanation of Section 2.10 on switchboards. It covers what a switchboard is, where it must be located, how it must be accessed, how it must be marked, and the many places where it must not be installed. End of Section 2.10. Clause 2.10.3 Construction. Clause 2.10.3.1 Access to live parts. This clause explains how live parts inside a switchboard must be arranged so that people cannot accidentally touch them. The idea is simple. Basic protection must come from covers, enclosures or barriers, just like we talk about in Clause 1.5.4. There is one exception for non-domestic electrical installations. In some commercial or industrial sites, live parts can be exposed, but only when access is restricted to authorized and trained people, and when the area can be locked or controlled so the public cannot get near it. If removing a cover or panel will expose live parts, then that cover must be clearly marked so anyone opening it understands the danger. This marking follows the requirements of ASNZS 61439.1. Domestic switchboards do not require this marking. Clause 2.10.3.2 Suitability. Switchboards must be strong enough to cope with real-world stresses. That includes mechanical forces, heat, electrical faults and anything in the environment where the switchboard is installed. A switchboard that complies with the ASNZS 61439 series, or the ASNZS 3439 series, is accepted as meeting these requirements. A switchboard must also meet these requirements if either of two things occur. First, the connected load at the switchboard is greater than 125 amperes root mean square per phase. Or second, the prospective short circuit current at the incoming terminals is greater than 10 kiloamps root mean square. Clause 2.10.3.3 Minimum clearances and creepage distances. Any bare conductors or live parts must be fixed in place with enough clearance or creepage distance in air. This spacing prevents accidental flashover or tracking between different phases or between phase and earth. The distances must match the ASNZS 61439 series. Smaller clearances may be used only when the equipment is manufactured and tested to its own standard, or when the live parts are insulated from earth in a way that ensures safety. Clause 2.10.3.4 Orientation and location of fuses and circuit breakers. Clause 2.10.3.4.1 Orientation of circuit breakers. If more than one circuit breaker is mounted in a row, they must all operate in the same direction so that the off and on positions are clear and consistent. You must always be able to see which position each device is in. Clause 2.10.3.4.2 Location of fuses and circuit breakers. Fuses and circuit breakers must be placed so that their purpose and relationship to each circuit is obvious. They may be installed on the back of a panel or escutcheon only in specific situations, such as when used solely as a fault current limiter or when used for control or instrumentation equipment. Combination fuse switch devices may also be mounted behind a panel if they can still be operated safely from the front. Clause 2.10.3.5 Screw-in fuses. Screw-in fuses must be installed so that the center contact connects to the supply side of the base. This prevents accidental contact with live parts. Clause 2.10.4 Bars. Clause 2.10.4.1 General. Bars must be designed so that conductors can be securely terminated. They must follow the requirements in Clause 3.7. Clause 2.10.4.2 Tunnel-type terminals. Tunnel-type terminals that take a conductor directly must not damage the conductor. Terminals must have one of the following: 2 screws, or 1 screw with a diameter at least 80% of the tunnel diameter. Tunnel-type terminals used for the main incoming neutral, the main earthing conductor, the earthing connection, or the neutral bar including the PEN conductor must follow this requirement. Clause 2.10.4.3 Neutral bar. Any switchboard that has a neutral conductor must have a neutral bar that can safely carry the neutral current. It must be positioned so every conductor can be connected without stretching or stressing the cable. The neutral bar must be designed so the incoming neutral cannot be accidentally disconnected. It must also have separate terminals for the incoming neutral and each outgoing circuit. When tunnel terminals are used for the neutral bar, the same rules from Clause 2.10.4.2 apply. Clause 2.10.5 Equipment identification. Clause 2.10.5.1 General. All equipment on a switchboard must be clearly and permanently marked in English. The identification must be easy to understand so anyone working on the switchboard can tell which switch or device supplies which part of the installation. Clause 2.10.5.2 Relationship of electrical equipment. Switches, circuit breakers, fuses and similar equipment must be labeled so their purpose is obvious. Clause 2.10.5.3 Bars. Bars must be marked to show whether they are active, neutral or earth. Domestic switchboards do not need this if the bar colors are clearly visible. Clause 2.10.5.4 Terminals of switchboard equipment. All terminals for incoming and outgoing conductors must be clearly marked so the correct conductor is connected to the correct circuit. The main connection and the connection for the main neutral conductor must be marked at the main neutral bar unless the neutral conductor continues directly through without a break. Clause 2.10.5.5 Common neutral. If one neutral bar is used for more than one circuit, it must be permanently marked so that each neutral conductor can be identified correctly. Clause 2.10.5.6 Fuse. If the fuse marking does not clearly show the rating must be marked either on the fuse, on the panel, or next to it. Fuses used as a group must be arranged so their ratings are easy to compare. Clause 2.10.6 Wiring. Switchboard wiring must be installed so it can withstand the heat and magnetic forces that occur during faults. Where panels need to be moved for maintenance, the wiring must be long enough to allow safe movement, must be held in place to prevent strain, and must be arranged so cables are not crushed behind the panel. Clause 2.10.7 Fire protective measures. Switchboard wiring must be installed in a way that slows the spread of fire. Openings into the enclosure must be sealed so flames or smoke cannot pass easily through. Any hole larger than 5 mm must be sealed with fire-resistant material. Larger conduits and wiring enclosures must also be sealed to prevent air movement that could spread fire. That brings us to the end of Section 2. You can see that this section sets the foundation for electrical safety, from how we protect people against electric shock, right through to how we install and position switchboards. If you understand these ideas well, the later sections of the standard will make a lot more sense. Thanks for listening, and when you're ready, we'll move on to the next section together.